Hello guys, and it's Genius File Studios again with another video. Today we'll be talking about the hierarchy of our universe. Our universe is really huge, and we are unable to understand, humans are unable to understand the actual size of it. We just think that it's big, so it's big, but we don't understand that how big it actually is. So today we'll be covering up all of that. And before we start, please like, subscribe, and press the bell icon so you can get new videos. Because Genius File Studios is always on the run. First, We'll be starting at the bottom, not the really bottom, but at the close to bottom part of the hierarchy of our universe, of what we know of our universe. So, our universe, we'll first start off the radius. The radius of our solar system is it's not showing it over here, but if we were to get a good picture, I'll join another diagram on the side here. So if you read the article, which I'll put in the description section for the Genius Fall Studios channel, there is a huge cloud called the Oort cloud, which is made up of comets, dust, ice waste, and all this other waste that was formed during the first creations of our solar system. All the waste from the birth of our sun. Then our sun, which is a really small portion of it, but is the hugest object here, and then the solar system around it. So it kind of looks like an eye if you look carefully. So this is our solar system. Now back to the radius. So the radius from the sun to the boundaries of the Oort cloud is about 1.72 light years. Yes, 1.72 light years. If you don't understand that, it's about 89 astronomical units. And if you don't understand that, it is about 7.3434 billion light years. Billion miles, excuse me. Billion light years would be almost the size of our universe. So it's billion miles. But you'll be saying that 7.34 billion miles kind of does make sense, but how does 1.72 light years be equivalent to 7.34 billion miles? But let me explain you that. We will talk about human technology to help us understand more about this. Voyager 1 is a perfect example for this. Voyager 1 was launched in the 1960s by NASA on the Kennedy Space Station and is currently, if I continue drawing and we continue increasing the size of this, if you've read in the article, it's a 50-50 theory known as the heliopause. This is believed to be the place where light loses its kinetic energy from the sun and stops in a way. So right now, we believe that Voyager 1 has passed this, and this is about 2 light years. And it's been launched in the 1960s, and currently it's 2020. So you'll be wondering, how come it takes for only 2 light years? It takes more than 60 years, more than 60 years. So now you can understand more about how big our solar system is. But let me go a little bit deeper into this so you can understand more. If you want to know the speed of Voyager 1, it goes at a speed of about 32,000. Let me get some space. It goes at a speed of about 30,000 meters per second. And if you're a customary dude, it will be about 90,000 feet per second. And 90,000 feet per second feet is about 5 Mount Everest stacked right on top of each other, just like that. So this is about 90,000 feet, and Voyager 1 travels at this speed, at this length per second, about this height per second. And yet, at this speed, after more than 60 years, has it reached outside the Oort cloud. So this shows the actual size of our solar system. But this is a really, really small portion of our actual solar system, of our hierarchy of the universe. Now you'll be moving one stage up into the hierarchy and going to our sun's local neighborhood. So this little circle you see around, which is known as our sun here, that's not the sun. That's not the boundaries of our solar system. That is the Oort cloud. So that is already the radius of the circle is already counted as 1 light year. Then from our sun to the nearest star, which is Proxima Centauri, which is slightly smaller than our sun because it's a red dwarf and our sun's a yellow dwarf. Another fact about Proxima Centauri is that it's in a 3-star cluster known as the Centaurs, and both of these other stars are blue giants. One is Proxima Centauri A, other one no, excuse me. One is Alpha Centauri A, and the other one is Alpha Centauri B. So that was just a fun fact, but um, the distance between our sun and Proxima Centauri is about 4.2 light years. So in Voyager distance, it would take more than 200 years for it to travel this distance. And the radius of our sun's local neighborhood is about 25 to 150 light years. So now this is way past Voyager distance, the speed of Voyager, so we'll just totally ignore Voyager now. But please keep that in mind because it's a good fact to remember. Now we'll be moving on to one more stage into the hierarchy, into the Milky Way galaxy. The Milky Way galaxy is a really, really huge chunk. It's really, really big. And it's a spiral galaxy. We all know that. So because it's a spiral galaxy and it's really huge and there's so many celestial objects in this galaxy, we separate the galaxy into different categories of arms. So we have like Perseus arm here, Sagittarius arm here, the normal arm here. And our sun is located on the Orion spur, which is this not so major, not so bolded arm, like for example, this arm over here. So it's not so bolded as that, but yet our sun is still on this arm. So this is what we are located on this arm, and the radius of our galaxy is about 52,000 to about 100,000 light years. So this shows the height, the length, the radius of our galaxy and how huge it is. But even though at now we're reaching the 100,000s for light years, even though at this measurement, it is still a really, really small portion of our universe. So now we can go one more stage higher into this, and we'll talk about our local galactic group. Our local galactic group is more of where our Milky Way galaxy is. So our Milky Way galaxy is one of the two biggest galaxies in the local galactic group. So we have the Milky Way galaxy, and then we have the Andromeda galaxy. The Andromeda galaxy is slightly bigger. And because these two galaxies are bigger and they have a more stronger gravitational pull, there are these other smaller galaxies orbiting around it, which are dwarf galaxies or small minor nebulas. Same thing with Andromeda galaxy. But even though they're dwarf galaxies and minor clouds or minor nebulas, each one's radius is more than 10,000 light years. So don't misunderstand small meaning as small as an ant. Anyways, the radius of our local galactic group is about 10 million light years. About 10 million light years. So now we're in the 10 millions, in the millions for light years. And a fun fact to know is that there's a theory that states that in a couple thousand years, maybe a million or maybe even a billion years, our Milky Way galaxy and our Andromeda galaxy, both because of their gravitational pull, and the other small dwarf galaxies galaxies' gravitational poles, both of these galaxies will collide, creating an ultramassive galaxy. We're not sure if Earth will be destroyed or if it will continue to prosper. So that's just one fun fact that you can keep in your brain while we're doing this. Now we're going to be going to one stage higher into our Virgo supercluster. Our Virgo supercluster is a supercluster, and it's named the Virgo supercluster because the biggest cluster here is the Virgo cluster. Our local galactic group is about a pixel on the screen now, so this has increased by a gazillionth compared to our local galactic group. The radius of our Virgo supercluster is about 53 million light years. 53 million light years. And yes, now we're in the 10 millions again. Because there's so many celestial objects, so many galaxies, so many nebula, so many clusters, so many Virgo superclusters, scientists are unable to find a name for them. Because if the main stuff which have names are usually have some type of important significance to our universe, or were like the first ones to be found of their kind. So that's why they actually have a name. But the other celestial objects which are important but are not so important are named after letters and numbers. And this also shows the outnumberance of names for celestial objects in our universe. And this, I'm sure you guys will be tired by hearing this, is still a really small portion of our visible universe. I'll talk to you later about that. Now, we have entered the local superclusters. So the Virgo supercluster is now this area right here, this small piece of area over here. And the radius of our local superclusters of this piece of area, piece of land, you can say, where our local superclusters lay on, is about 400 to 600 million light years. So now we're in the 100 millions for light years. 400 to 600 million light years. I apologize for the messy handwriting, but that's how it is. Anyways, there's so many superclusters that, and each one has like a pretty unique name, like the Ursa Major supercluster, the Columbia supercluster, Sexton supercluster, um, Capricornia supercluster. And if you look carefully, you'll see these voids, like the Boots voids. So these voids are just empty areas of just plain black matter, dark matter, mainly dark matter, and there are just usually just dwarf galaxies and dwarf nebulas and dwarf stars, dwarf solar systems, and really small galaxies just there. So that's why, but there's mostly just dark matter. So that's why they're called voids. So they're just empty areas. And now we are right now on the second last part of the stage, second last stage on the hierarchy of our universe for what we know. And now we're going to be going to the last part, which is now our observable universe. It's called the observable universe because our universe is really huge, and we due to the, if you've read in the article, the redshift, which is a Mother Nature's barrier which prevents us from looking farther out than this boundary of the observable universe. That's why it's called the observable universe, or what we can see of the universe. Otherwise, the universe is billions and billions of times bigger. And if you saw in the other pictures, we can see that we are usually in the middle of everything. We are in the middle because our infrared technology, which helps us look at everything in our universe, works in a radar format. So it goes in circle by circle by circle in a radius and diameter way. So the radius and diameter is equal, so that's why we're technically in the middle. But if this for the whole universe, we could be here, we could be here, we could be here, we could be here. Or we could actually be in the middle, which is not so likely, but we could. So that's why we are technically in the middle. The diameter of our observable universe is about 96.03 light years. no, 96.03 light years, because that would be about as big as our sun's local neighborhood. It's about 96.03 billion light years. So that is pretty much it about the observable universe, and this is just a really detailed drawing about what scientists believe our observable universe actually looks like, and this is just a diagrammic format. Anyways, thank you for watching this video, and I hope you liked and subscribed this video, and I and yeah, I hope you see the next video, and I hope I see you guys soon, and bye bye.